Following the success of GPT-1 and BERT, researchers started to scale up large language models. And as they did so, they started to notice a crucial capability of large language models emerging. And that is that LLMs can just follow textual instructions. And this is a really different paradigm compared to how people did machine learning prior. So the prior paradigm is that labeled data that defines the task. So imagine you want to do image classification. You want to perform classification between dogs and cats. Well, what is a dog? What is a cat? Well, you can't explain what that is to a neural network. The way you define that task, the way you define what a cat is and what what a dog is, you provide labeled images. So labeled data that defines task. What is a spam email versus a non-spam email? You provide data defining what is spam and what is not. So this was the paradigm prior to sufficiently large language models. Self-supervised pre-training on large unlabeled text would improve the efficiency, but labeled data was needed to define the task. For sentiment analysis, you had to provide paragraphs that are labeled as positive, paragraphs that are labeled as negative, and that kind of labeling would define the task of sentiment analysis, and it would define the notion of what is a positive review and what is a negative review. But the new paradigm is really much more human-like. What you do is you define the task by just saying what it is. You just provide a natural language description defining the task, and the language model would understand. Researchers gradually crystallized this paradigm through the research in GPT-2, GPT-3, T5, FLAN, and Flan-PaLM. The GPT-2 and GPT-3 papers have very similar titles and very similar messages. If we read the title of the GPT-2 paper, it reads, Language models are unsupervised multitask learners. GPT-3 title, Language models are few-shot learners. These are very similar sounding names. Indeed, the messages are quite similar, and also the architecture is very similar. GPT-3 simply scales up GPT-2 and achieves stronger results. And in fact, the architecture didn't really change much since GPT-1. So for GPT-1, 2, and 3, the model size increased at the rate of 120 million, 1.5 billion, and 180 billion. GPT-1, 2, 3 has also increasing data size, 40 gigabytes, 4 gigabytes, 40 gigabytes, 600 gigabytes. The main message of the GPT-2 and GPT-3 papers was that GPT can solve many tasks with a unified task-agnostic architecture and without even supervised fine-tuning. Task-specific training data is not used, so it's zero shot in this sense. Or when task-specific training data is used, only a few is used during inference, and so this would be few shot in context learning. I'll define these terms in the next slide. So no task-specific training data is used for training or fine-tuning. These were used in GPT-1, but it turns out in GPT-2 and GPT-3, this kind of task-specific training data is not needed. Now, that is not to say that task-specific training data is not helpful. They are helpful. It is helpful as the T5 and Flan T5 papers later show. But GPT-2 and GPT-3, it demonstrated that task-specific training data is really not needed. So for comparison, the Elmo model is really not at all task agnostic because Elmo is really should be thought of as a trainable tokenizer, and then that trainable tokenizer is attached to some sort of RNN mechanism that solves a particular NLP task. BERT and GPT-1 are more task agnostic architectures, but these still had task specific heads that were attached for the fine-tuning purposes, and you needed task specific training data. But GPT-2 and GPT-3 relies on zero-shot or few-shot in context learning. Let me define these terms. Few-shot learning traditionally refers to a model learning a behavior with only a few labeled samples or demonstrations. So classically, few-shot learning would have a pre-trained model that's fine-tuned via gradient updates on a few labeled data points. So then zero-shot learning would mean performing a task with no demonstrations. Now, how could this even be possible? Well, here's how GPT-2 performs summarization in a zero-shot manner. The authors say that to induce summarization behavior, we add the text TL:DR. So this is the abbreviation of too long didn't read. And this is the kind of text that you would write usually that a lot of people would write before providing a summarization. So the authors of GPT-2, they added the text TLDR after the article and generate 100 tokens with top K random sampling. So it turns out that GPT-2 can perform summarization without any explicitly paired summarization dataset. Usually, to teach summarization to a language model, you would have to pre-train the language model on a large corpus in a self-supervised manner, and then you need to prepare a summarization dataset where you have, let's say, a bunch of articles and their paired summaries. And then you would fine-tune the model on this paired article summarization dataset in order to define the summarization task. Now, granted, GPT-2 is trained on a large corpus of text, and some of that text would probably have some sort of summarization in them. But nevertheless, the authors of GPT-2 did not explicitly need to prepare a summarization dataset. It was just part of the pre-training data. And then you can just tell the model through this nice trickery you can induce the model to perform summarization, even though there was no explicit effort to have the model be capable of performing summarization. In-context learning, abbreviated as ICL, is a capability first explicitly reported in the GPT-3 paper. And in context learning, the model discerns the task implied by the context of demonstrations with or without explicit descriptions. So here's an illustrative example. So this is a non-ICL task. So this is just standard next word prediction. The quick fox jumps on the lazy blank, and then the completion is dog. There's no in-context learning in this. This is just standard next token prediction. Whereas in in-context learning, if you provide this input text to a language model, rose colon red, sunflower colon yellow, lavender colon, if you were to show this to a human being, the human being would infer from the context of these two prior demonstrations, that what's being asked for here is the color of the flower, lavender. And indeed, that's the task that is being implied, and the answer is purple. And if you feed this to a language model, something like GPT-3 or anything more powerful, it would be able to solve this task no problem. The language model will understand what you're asking for through this context by performing in-context learning. ICL, in-context learning, can also be applied with arbitrary rules. So here, we just make up this rule, xy, comma, yz, comma, at, comma, xy, yz, yz. A, B, C, D at, A, B, C, D, C, D. Okay, so now the rule is pretty clear, right? So MN, at, this should be MN, OP. Well, the rule that's being applied here is clear to a human being when a human being reads this, and it's also clear to a language model. The language model, something like GPT-3, has no problem solving this ICL task. Here's another ICL example that's perhaps not as obvious. So here we have the word banana, arrow, manzana, car, arrow, bicicleta, and grass, arbol, and coffee, arrow, something. So I actually don't know Spanish myself, so I had to use a dictionary to construct this example. But on the left, we have English words, and on the right, you have Spanish words. And if you don't know Spanish, you might think that this is a simple translation task. But if you know Spanish, then you would notice that this is not a translation task, because manzana is not the translation of banana. Bicicleta is not the translation of car. Actually, if I ask ChatGPT o1 to solve this, it provides a perfect answer. So here's the rule that it infers. Well, banana is, of course, a fruit. And then the word on the right is manzana. That's Spanish for apple. And then on the left, we have car, and bicicleta. That's Spanish for bicycle. A grass, that's the English word, and arbol, that's Spanish for tree. So the rule is we take the English word on the left, we find something different but within the same category, and then translate that word into Spanish. So what should coffee get mapped to? Coffee is the English word for a beverage, and then tea is another beverage within a similar category, and we translate that to Spanish, and we get té. So ChatGPT returns té as the answer. And in my mind, this is a perfect execution. This is a perfect solution to this in-context learning task. But actually, the earlier paper, GPT-2, had hints of in-context learning capabilities. Here's a quote from the GPT-2 paper. Similar to translation, the context of language model is seeded with example question-answer pairs, which helps the model infer the short answer style in the dataset. The term in-context learning, it refers to the LLMs, the large language models' ability to learn the user's intent through examples within the context of the text without any parameter updates. You show a handful of demonstrations, label data points, and ask the model to follow the examples. And this is how GPT-2 and GPT-3 can solve a wide range of tasks in a few-shot learning manner without performing any gradient updates. Again, to re-emphasize this point, in-context learning refers to performing learning without performing any parameter updates. So there are no gradient updates, there's no backpropagation, there's no SGD, there's no atom. The parameters are not being updated. Now, you might find this kind of terminology to be a little bit jarring if you associate learning with performing backpropagation and performing parameter updates of your neural network. But what the authors are claiming by using this terminology is that in-context learning should also be thought of as a kind of learning. It's just that parameters, neural network parameters, are not being learned, but it should still be considered as a certain kind of learning. ICL is a crucial capability because most natural language instructions in real life that humans give to other humans, they actually do not specify all the details with complete precision. If you've ever had to do paperwork within an organization, you probably have this experience of receiving a certain form, being kind of confused as to what needs to be done for this form. So you ask for a sample, and then you receive a sample of somebody else filling the form out for some other purpose. And looking at the sample, you understand, okay, this is what I need to do with this form. In natural human-to-human communication, it's actually quite rare that full specifications of orders are provided. Humans are not computer programs, and we usually understand certain requirements or orders through the context and through the examples. So it's important that language models understand what you mean through examples, and through in-context learning, you can explain a lot of things with pretty good precision without having to lay out all the details in a almost legal or programming language like document. You can just show a few examples, and that can be used to steer the behavior of a language model like GPT-2 or GPT-3. The T5 model is the abbreviation of the text-to-text transfer transformer. It doesn't exactly roll off your tongue. The T5 model uses an encoder-decoder transformer and formats all pre-training and fine-tuning into a text-to-text format. The design goal of the T5 model was to produce a unified task-agnostic architecture. T5 is meant to solve many tasks, which are not necessarily semantically related, all formatted into text-to-text format. So you would have the same model, same objective, same training procedure, and same decoding process for every task that you would consider. So the T5 model was pre-trained on a large corpus of unlabeled text with diverse objectives inspired by prior work. So you have a language modeling, something akin to next token prediction. You have the BERT style mass language modeling, and some other self-supervised pretext tasks. And in all cases, the input is fed into the encoder block, while the target text is generated by the decoder one token at a time. And then after the pre-training is done, T5 is fine-tuned, and is fine-tuned simultaneously on a wide range of tasks. But T5 is one model, so how can we have T5 perform a wide range of tasks? Well, the way we do it is we simply prompt the model differently for each task to inform T5 of the specific task to solve. So here we have translate English to German, that is good. And then by looking at this prompt, the T5 model knows that, okay, well, what I need to do is translation, so I will output the translation. Then here we have COLA sentence, the course is jumping well, not acceptable. So looking at this, the T5 model notices that, okay, this is the COLA task. The T5 model looks at this and this says STSB sentence 1. So this tells us that the T5 model well, this is the STSB task. So, well, it outputs an appropriate output. Summarize. So this is summarization. This tells the T5 model that, well, okay, then the task is to summarize this paragraph, and it provides a summarization. So the T5 paper was also a landmark paper that advanced the state-of-the-art with the pre-train then fine-tune approach. And this paper also further demonstrated the idea that language models can understand and respond to natural instructions. We can simply tell a language model what we want, and it will follow our instructions. However, there are some problems with the T5 prompting. The prompts that were used were unnatural, as they did not fully describe the task at hand. If you look at this, what does COLA sentence mean? Well, if you know the specific COLA task, if you're familiar with the natural NLP literature, then you might know, but well, this is not a full description. What is STSB? Well, again, if you're within the NLP literature, then you would recognize what it means, but here, this is not a full description. So really, what's being done here is a halfway measure being a fully arbitrary label. So imagine labeling all the tasks at task 1A, 1B, 1C, task 3A, 3B, 3C. So these would be arbitrary labels. So that would be one extreme. And the other extreme would be a fully natural language description. What's being done in T5 is something in between. But what we really want is we should really be providing a full natural description describing the task at hand. So this leads to instruction fine-tuning. The idea of instruction fine-tuning was presented in the Flan paper and the T0 paper. And the idea is to fine-tune a pre-trained model on a collection of data sets described via natural language instructions. So here we have a perfect unification. For the summarization task, instead of just saying summarization, we give a full natural language instruction. How would we rephrase that in a few words? For sentiment analysis, we explicitly say that what's followed is a review. So this review says something about a certain establishment, and then we have the question fully phrased in natural language instruction. On a scale from 1 to 5, I would give this establishment a, well, in this case, 4. And question answering. The prompt is, I know that the answer to the question, what team did the Panthers defeat, is in the Panthers yada yada yada, so a paragraph is provided. So we even tell the language model what the question is, and we tell it that furthermore that the answer is within this quoted text. Can you tell me what the answer is? And then the language model provides the answer. And in this sense, we achieve full unification. All natural language tasks now all become subtasks of the meta task of following the natural language instruction. Now we have built a language model that solves one task. This one single task is to follow natural language instructions. And in fact, we can have this kind of zero-shot generalization. So in this natural language inference task, we ask, suppose the banker contacted the professors and the athlete, and then we ask, can we infer that the banker contacted the professors? Even though the T0 model was not trained on this kind of natural language inference task, this natural language inference task, the way it's prompted, it is part of the task of following natural language instructions. So the T0 model is actually able to solve this task and provide the correct answer yes, despite never being trained or fine-tuned on natural language inference tasks. The Flan model is a 137 billion parameter model, instruction fine-tuned on over 60 NLP datasets, with instructions verbalized via natural language instruction templates. So the 60 NLP datasets represents the common sense reasoning, translation, sentiment analysis, co-reference resolution. So we have a good collection of natural language tasks, and their instructions are verbalized via natural language instructions. So the Flan paper worked very well. So as a follow-up paper, the Flan-PaLM paper really scales up instruction fine-tuning. Flan-PaLM scales instruction fine-tuning to a larger model, a 540 billion parameter model, with 1,836 instruction fine-tuning tasks. So again, the overall template is the same as before. We have a wide range, 1,836 different instruction fine-tuning tasks. So we have a good collection, a good variety of tasks where the question is phrased as a natural language question. The language model is fine-tuned on these wide range of tasks simultaneously. And later on, after the fine-tuning, if the language model is asked a question about a type of task that it was not explicitly trained on, it can still provide a good answer because this is also just a natural language instruction. And now this language model is being trained to just follow natural language instructions. So a key finding of the Flan-PaLM paper is that task diversity is essential not just in having the model be multitask and multi-purpose, but also in benefiting the individual task performances. So let's say you are interested in performing task A. Let's say you're only interested in performing a translation between English and Spanish. Even if you only care about that single task, you should train on all the tasks A, B, and C, because doing so will improve the performance on task A. When performing instruction fine-tuning, a technicality is that the chat template needs to involve special tokens. So the special tokens, instruction message start, I am start, and instruction message end, I am end, these are used to format the conversation in a chat format. This trick significantly improves the LLM's ability to follow instructions and engage in turn-based conversations. So really, instruction fine-tuning coupled with the use of these special tokens, this is what allows a language model to serve as a chatbot. And by the way, the use of these special tokens it's not really optional. You have to do this, otherwise the performance is significantly impacted. So here's an example chat template. So I am start system. So the system prompt is, you are a friendly chatbot who always responds in the style of a pirate. And then we have, and then the instruction message is ended, message start, and this is from the user. The user enters the message. How many helicopters can a human eat in one setting? The human presses enter, and then the token, the special token I am end is entered to the language model. Furthermore, the special token I am start, and then assistant that's added to the language model. The language model then goes on to generate, just 6, and concludes. So that's the response produced by the language model. And then the turn goes to the user. So the user then asks, are you sure about that? The user presses enter, and then it continues on. So when you perform instruction fine-tuning at scale and use these special tokens, your language model gets converted into this helpful question answering chatbot. So if the user were to enter, let's say, the prompt question, what is the capital of France? If you press enter on this language model and had the language model continue generation before performing instruction fine-tuning, the language model would not necessarily answer this question. The language model might just continue with other questions. Question, what's the currency of France? What's the population of France? What's the official language of France? Because this kind of list of questions might have been something that the language model has seen in the pre-training data. So it would be natural to continue this question with other questions on the same entity, France. Whereas after instruction fine-tuning, if you write this question and press enter, well, first of all, because you've done instruction fine-tuning, when you press enter, the special tokens instruction message end, instruction message start, that will be inserted. So the special tokens will now be used. And also because the instruction fine-tuning data is structured in a way to have the language model be helpful and have the language model answer questions that are being asked, the response will be something like this. Answer, the capital of France is Paris. So really, after instruction fine-tuning, that's when the language model starts to really answer your question and really start to be helpful to you. And you no longer have to do this arduous in-context learning prompting in order to steer the language model in a direction that you want. After instruction fine-tuning, you can just ask questions and it will follow instructions. Hyungwon Chung is a research scientist at OpenAI. He's not as famous as Richard Sutton, at least not yet, but he's doing pretty good work. And he made a post on Twitter of the website X, and I found it to be extremely insightful, so I'm quoting it here. Chung says, a counterintuitive implication of scale. Trying to solve a more general version of the problem is an easier way to solve the original problem than directly tackling it. Attempting a more general problem encourages you to come up with a more general and simpler approach. This often leads to a more scalable method. By leveraging increasingly cheaper compute, you solve the specific problem as a byproduct of tackling a more general one. Some examples: directly solving natural language understanding tasks, such as question and answering, versus learning a general language model and solving the task as a next token prediction. Instead of directly working on machine translation, working on a general problem of learning all languages, it actually works out better. Hyungwon Chung, October 11th, 2023. Gradually, researchers have adopted a three-stage training process for large language models. Although this paradigm is slightly evolving with the advent of what people are referring to as mid-training, but this overall rubric is still in place. The first stage is pre-training. During pre-training, the language model is trained on a large corpus of unlabeled text in a self-supervised manner with the next token prediction loss. Pre-training produces the model with the base capabilities, but the resulting model just tries to complete text and it just babbles on. The model does not have the propensity to follow instructions or to be helpful. It just has the propensity to complete text in a natural way. And pre-training is the most compute-heavy stage of training the large language model. And then stage 2, which is referred to as part of the post-training process. So post-training refers to things that happen after pre-training. Stage number 2, instruction fine-tuning. So instruction fine-tuning induces the model to follow instructions and be helpful. The model can engage in a chatbot style dialogue after instruction fine-tuning is performed. And the third stage, RLHF alignment. This is also part of post-training. RLHF further aligns the large language model with human values and expectations. And RLHF stands for reinforcement learning with human feedback. So as the name suggests, it uses reinforcement learning. So far we've covered the foundations of large language model training. We've covered the pre-training stage. We've talked about the instruction fine-tuning stage. And this is a good point to conclude chapter 2. In chapter 3, we'll continue on with reinforcement learning with human feedback, and then we'll move on to reinforcement learning with verifiable rewards.